Safety Bravo. terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
SPS level?
Constant velocity
104.
accordion. Constant velocity accordion, altitude error.
We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
Throttle down.
Sky crane maneuver has started. About 20 meters.
Tango
off the
Delta.
orbit.
Nominal. We're getting signals from MRO. Remu stable.
UHF is good.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life. At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth. Perseverance is continuing to transmit.
Well, that was our scene earlier today when Perseverance landed on the surface of Mars, ushering in a new generation of robot explorers. Saxon, turn off the audio. Oh, that's not his audio. I was stupid enough to leave my audio on my laptop right now. The joys of physics Hollywood. Well, ladies and gentlemen, greetings, junior scientists, and citizens of this great, big, wild, weird, and wonderful world in which we live. As always, I am your humble science communicator, the Great Orbax, here located in Physics Hollywood at the Department of Physics at University of Guelph. And as we just saw earlier today, we managed to land the Martian rover Perseverance on the surface of Mars. Now, for those of you who missed our stream earlier, we were lucky enough to be joined in the afternoon by an incredible scientist, the lead instrument scientist on 3 of the previous Martian missions, Spirit, Opportunity, and Curiosity, the lead scientist for the APXS instrument, Dr. Ralf Gellert. We'll bring him back. He's here to talk to us this evening and to follow up with some of the stuff that we learned today.
Hi, Orbax. Hello.
How are you doing?
Good.
So have you been excited in the interim, the little bit that we've left you behind there?
Mm-hmm. Yeah, the blood pressure went a bit down again. Yeah.
Well, there was a lot of excitement this afternoon after the landing. We got some of our first images that were coming back, and we're giving people an opportunity now to hop on and to actually, if they missed this afternoon or if they've seen this, if they see this on the news, because apparently it's just been playing nonstop in the couple hours since we've left the stream. They have an opportunity to actually chat with us and to ask you some real questions about what's going on the rovers. So let's pop up a couple of those first images there, Saksham. For those of you who are new to our stream, Saksham Sharma behind the scenes is our producer. He'll be putting up some of the images as we call fit to bring them up. That's the APXS, which is not one of the first images on the actual, on Mars, but that is the device that Ralf had installed on the Curiosity rover. Effectively the first Martian selfie, is that correct, Ralf?
No, that's actually not a selfie. It's just the arm extended and the main camera looks at it. So that's not a selfie.
I guess it's difficult to define selfies in terms of robot arms.
If you go back to the image there, okay. On the other side of the rover arm, there is a microscope.
Okay.
And that is the camera that actually takes the rover selfies, because it has to get away from the rover itself. And then they move the arm in 50 steps and take an image every time. And then they stitch it together. That's the way they do the rover selfies.
Interesting.
Yeah, the old the old rover couldn't do this because the microscope had a fixed focus length, so it was all blurry.
Interesting. Well, I'm going to see if we've got some of these pictures here. I don't know if we've seen so far. We've got here the first of the images that's come back from the actual rover, and this came back within a mere matter of minutes from the actual touchdown. Can you tell us a little bit about what we're seeing here?
I would say you see grayish blur, but yeah, you get a sense of scale by on the right side the rover wheel. So this is one of the cameras. Okay. This is one of the cameras that is in the front, likely of the rover, and it's typically black and white because this is just for navigation, so hazard avoidance. If they drive automatically and see a big boulder coming up and getting closer and closer, then the rover computer will simply put the brakes on.
Interesting.
But otherwise, looks like many other places on Mars from this little.
From this vantage point. We've got another picture here. This is the second one to come in, and it's interesting here to see the shadow of the actual rover in the foreground there.
Mm-hmm. Yeah, I was astonished by, in the foreground there are 3 flat rocks, and then I saw it on the web in higher resolution. The group of rocks behind it, they are oddly shaped. So looks interesting. Both flats means something, might be an outcrop that is there, and the other ones look kind of weird to me, at least.
Well, that we did establish earlier that you weren't a geologist. That's correct.
Exactly, yes.
That's the statement of those being weird-looking rocks. Well, we have so much to talk about, things that we can chat about. I don't really know where to start. So there were a couple things that we didn't get to this afternoon that I thought were really interesting that maybe we could chat about this evening as we get more and more viewers on the stream, and we can talk about, get some of their questions as well. But one of the big things that we discussed this afternoon was this 7 minutes of terror. We talked about this idea of the entry and the descent of this this rover. I'd like to show that video again, Saksham, if we could, of the Perseverance rover landing. And I wanted to compare it to previous missions, such as the Mir landing that we had. For those of the viewers who might have missed this afternoon, Ralf, can you take us through this kind of video as to what's happening here?
Okay, so you're arriving at Mars with about 20,000 kilometers per hour, and you're touching the top atmosphere, and with friction you are slowly slowing down. That's the heat shield, and at some point when the heat shield cools down again, has dissipated all the abraded energy, you throw out the parachute. I mentioned it. This is deployed at 2 times the speed of sound, and during this time, you throw away the heat shield. With one of the previous rovers, we actually visited the used heat shield with Habitability. Then you release the rover with the backpack, the sky crane, And at this time, you have radar that tells you how far away you are. And I've read it up. The new one has also hazard avoidance in this space. So if they see a very cratery terrain, they will try to avoid it. At some point, the bridles go down. Whenever the rover touches the surface, the bridles are cut and the sky crane flies away and crashes somewhere in the surrounding. Most important thing is not on the rover.
Yeah, I would say that's the most important thing. Now, as we watch the landing taking place through mission control, it's interesting you mentioned that hazard avoidance, because I saw that there was an actual last-minute trajectory change on the descent for the hazard avoidance. They mentioned it anyway.
Really? In which phase?
I was all coming so quickly, but they mentioned it in the actual video. If you watch or replay that, you can see that they do an adjustment or a small change. Yeah. So this system that Perseverance landed by with the sky crane, this existed for the previous Curiosity rover as well, right?
Yeah, it looks essentially the same. And
for Opportunity before that?
No.
So Opportunity is one of these so-called MERV, or Martian exploration rovers with that
Martian exploration rovers, yeah.
So we have an animation of the way that those were landed as well. Now you've designed, for our viewers who don't actually know you or missed this afternoon's stream, you were the lead instrument scientist for the APXS that was on the last 3 rovers, correct?
Yeah.
And can you explain to our viewers what that device is and your involvement with that?
Yeah, actually, you showed an earlier version, the photo of the MER APXS.
Oh yeah, well let's bring that up, Sachin. There we go.
Exactly, that's it. So that's the earlier version of the APXS, and this is
what year is this?
That was 2003.
Oh wow.
Yeah. And this was already an improved version of the APXS that was on Mars Pathfinder, landed in 1997. And this whole instrument was developed at the Max Planck Institute well before my time. And I joined the Max Planck Institute and the University of Mainz in 1999, when they had these upcoming missions on the horizon. And my task was to help the lead scientist at that time, Rudy Reeder, who worked for 20 years on that instrument and designed the MER APXS, helped to improve it from the Pathfinder instrument. And it got a new SDD, silicon drift detector, much higher resolution for the X-rays. And this instrument, if you show it again, the image, because you can see actually the business end of the instrument.
Now, for scale, what size is that aperture at the
The diameter of the outer aluminum exactly fits in an airplane Coke can.
Wow.
Because that was Rudy's original idea, to slide a Coke can over the outer side and make some advertisement with that.
Oh, really? Wow, that's forward thinking.
NASA didn't like it.
No, didn't care for it. Well, that's an interesting thing to point out, though, because we often see images of these rovers with little or no perspective as to the size of them. It's interesting that device, or that cylinder for that, is just the size of a Coke can, that basically that whole device is maybe the size of a camera sitting on that external arm.
This one has a different shape, but it's essentially smaller than a coffee cup.
Wow.
Cup. Yeah.
So
and
as we mentioned,
400 grams or so.
We mentioned earlier that the rover itself is probably about the size of a small vehicle.
Yeah.
And it's weighs much less though, probably about a quarter of the weight of a car.
No. I think Curiosity is 600, 700, 800 kilograms. So a smaller car.
Yeah, a compact car is about 4,000 pounds. So,
which is
1,800 kilograms ish.
Okay, I'm from Germany. There, the cars are
yeah, much smaller, more efficient cars. In Canada, all of our vehicles are way too big. You can tell. But yeah, so when you're dropping something that size on the surface of a planet that has a lower gravity, that has less atmosphere than Earth, this sort of fitting with these retro rockets and these boosters to bring it down is a pretty, I would call it sophisticated way to land something. Whereas on the original, the MER rovers, it was it seemed a little bit more brute force way of sort of dropping it on the planet.
Do you have the animation?
We do have the animation. Saksham, do you want to take us through that animation, Ralf?
Oh, yeah, for sure. So this is the earlier version of the landing. So the very first steps are nearly identical. But for example, you see there are no engines in this phase that steer it in the right direction. All these steps made the landing ellipse a little bit smaller. So until here, everything is like before. You eject the heat shield, but now you have the whole rover folded up in huge airbags that you at some point inflate, and that's about 4 or 5 meters diameter.
Oh, wow. Okay.
So now you cut the bridle after 3 or 4 meters height, and then that thing bounces and bounces.
The sizable bounce. Now, is that because you're dropping? I guess it's a combination of the fact that the gravity is less and you're dropping it from quite a height, I suppose.
Yeah, I think it's below 10 meters, but
really? Wow.
You're dropping a couple of tons down there. But then at some point, and that's a tricky thing. Now you deflate the airbags, and this 3-pedal must unfold so that the rover points upwards and not sideways.
Absolutely. So this is the thing that sort of sets me back, is that how do you orient or set this up so that it always is right side up?
The landing stage where the rover is strapped onto has to make the decision, okay, what's the order of the 3 paddles that it extends to actually get on in the right position?
Okay, so that's all automated on board.
It must be, because you can't talk to Earth because the antenna is still in the shell.
Right. Okay.
Yeah.
So this is a pretty risky gamble, I guess, once you're on the surface.
Okay, but first it worked. And have you seen the earlier version where you throw out a rocket backpack? So it's for free there.
Well, okay, so my follow-up question was something like this. As somebody who's designed and worked on an incredibly delicate device that's strapped to the body of this thing, is there worries that it's not going, that on the landing you're going to shake it loose, or that it'll be non-functional once this entire thing opens up?
Actually, the very first bounce that we've seen here at the land, and I like this, how elegant the front wheels unfold here.
Mm-hmm.
Looks like ballet. Voila. The very first bounce is really unique, and all the challenges you have to go with your built instrument through a qualification program. And for example, for the vibrations that the rocket does during launch, you simply put the instrument, for example, the sensor head that you've seen, you put it on a huge loudspeaker and actually dial the volume up. And you shake the hell out of the instrument, and you see that everything works after you do this. But with the first bounce, which is unique for the MER rovers, they actually had a so-called shock test where they put, so the vibration test is essentially a certain spectrum of motion with certain acceleration, and the random vibe that you get during launch is done with a loudspeaker, but the shock test, they couldn't find a loudspeaker that has this profile of a...
Sure, yeah.
So the test there was to put all the instruments, screw them on a metal stainless steel table, and then 5 or 6 centimeters possibly beside it, really let another metal fall onto the metal table. So like a hammer, you test this unique first bounce as a shock test with a metal table, and you hit the stainless steel table with another hammer, and then you adjust the violence to what you expect from the airbag landing. Yeah, this is how the old MER rovers worked. They had a brush and grinder.
Okay.
So you were able to grind a little bit in a couple of millimeters into basalt. This is the camera, a fixed focus black-white camera with a poker to keep the distance. You take images, which are the favorite images of geologists. And then on the other side, yeah, to the left here, there you see the APXS that you saw in the photograph before. So then you rotate through all the instruments to the back here. There is the Mossbauer spectrometer, which determines the mineralogy. So these were the close-up arm instruments on the MER rovers.
Very interesting. Well, it's funny because it does seem somewhat crude, but I mean, as you mentioned, it works. I mean, you're dropping it in a bag of balloons, and then you're testing your equipment by just smashing giant hammers beside it. But I mean, if it can put up with that kind of rugged environment, then it certainly can put up with a rugged environment on a separate planet.
Yeah, and the MER landing was actually used also by Pathfinder.
Right.
So they shrunk, or they folded together the MER rovers. You saw the unfolding.
Yeah.
They cleverly fit the MER rovers with essentially inactive landing station into the original Pathfinder landing, where the original Pathfinder had a lander which did all the communication, and then a tiny rover which couldn't talk to Earth and could just crawl around the landing base station. So they merged everything more or less, boiled down the Pathfinder landing station into a just landing structure, and put all the communication, all the capabilities into the MER rover itself, which then could talk with Earth and could move. And it actually turned out, you see the MER rovers had these unfolding solar panels. And originally, the duration of the mission was planned for 90 days, 90 Martian days. And they were fully expecting to see a lot of dust settling on the solar panels and actually making your power supply worse and worse. But it turned out that, yeah, for example, the inactive, not moving Pathfinder lander, it got dustier and dustier. It didn't move. And therefore, it actually lasted something a couple of months, 4, 5, 6 months or so. But MER rovers, with the same technology, solar panels, they lasted over several winters simply by first moving. And I expect that when you drive across the landscape there, you're shaking off a little bit of the accumulated dust. And then sometimes we got a strike of luck where the wind actually cleaned the solar panels.
Right, yeah, for sure. And then it actually gives you another chance to revitalize the system.
Exactly. And during the winter, you simply park the rovers tilted to the North Pole, so that you get more of the lower standing solar energy of the sunlight. So this is how they lasted so long. And
amazing.
The Opportunity rover lasted till 2018, and it was only taken down by the biggest recorded dust storm in history, where within 2 or 3 days the solar irradiation went down by, I think, a factor of 100. So there are images where they looked at
literally the worst case scenario that you could have for a system that runs on solar power.
Exactly. They took images where they looked at the sun, took a picture, and then the next day they took a picture, and you see it gets darker and darker a little bit, and then pitch black. So they couldn't literally see the sun during the day, during this dust storm.
Wow.
And that's of course bad news for a solar-powered rover.
100%. Now, all the current rovers, solar power is the only way that you're going to get them to continue on. This new Perseverance rover is pretty loaded up with a whole assortment of different scientific instrumentation. And as again, I hate to repeat this, but this is again for people who might have missed our earlier stream. The purpose here for the mission of Perseverance is to try to find if there's any sort of, basically to answer the big question, was there life on Mars? Or to at least see if they can find any samples that have microbial life or the remains of microbial life inside of it. Now, we had a discussion this afternoon, which if people want to check out, the previous live stream is on YouTube now. And again, I'd like to remind you, if you have any questions, feel free to ask them in the chats, and we'll get to them as we can. But one of the things that the new rover is doing is it's actually drilling out core samples. So we managed to get an animation from NASA of how that core sampling works, and I thought maybe it'd be a nice addendum for you to walk us through that. I know I keep throwing animations at you that you may have not seen so far, but Factor, we have that drilling footage.
I haven't seen this animation of the core yet.
Yeah, it'll be interesting, especially compared to the old system that was a grinder with a brush.
Yeah, and Curiosity had a percussion drill.
Right. So all of these, for the uninitiated, the purpose of all of these devices is to get samples. Whether we're looking at samples in the form of dust, whether we're looking at them as solid rocks, or portions of much larger rocks, the idea is to get samples to then do scientific testing and to find out what the composition is.
Look at that monster arm. Holy
It's huge.
Yeah.
So I also noticed that there's a little bit more of what appears to be a suspension system on this rover compared to the much earlier ones. That the
What do you mean suspension for?
I mean that the wheels seem to be much further away from the actual body of the rover. But you're saying that this is pretty much the exact same chassis as Curiosity has.
It should, yeah.
So this is the core samples being taken and stored for later use.
Ah. Oh. Okay, now I know how they use the freed up space where there were the two instruments in the rover's body. Of course, yeah.
So presumably this is a collection of these core samples that are going to be picked up at some later time.
Yeah, I always thought they just drop it directly when they collect it. No, that seems a very sophisticated system for collecting these cached samples. But
it does. So now those samples themselves, these cached samples, the tubes that hold the actual collected samples in them, are they being tested on as well, or are they kept preserved for later pickup, and then we're just testing areas near them or around them?
Honestly, I don't know, but I would expect that possibly they do something like they have a nice rock that they look from the surface, tested what it's made of, so they have an idea. Possibly they drill one core and present it more or less like on a stage, so that they can take images of the interior of the core, because what geologists are always after, so the ideal sample for a geologist. I haven't seen any geologist that isn't fond of thin sliced rock samples.
Yeah.
And they look at it under polarized light, where all the minerals look different. And they can read from these highly magnified images a lot how this rock was formed. But the idea, and we 15 years ago, the original plan was for the Curiosity rover as well to not have a percussion drill, but a core that you can put on a plate, can take images with a microscope. We can drive along the core. If it's 10 centimeters long, you can see, okay, that's the top. This is the composition on the top. This is in the middle, and that's deep in the rock. And then to feed this rock into the analytical instruments, they put this core into a crusher. So they first extract the core, you investigate it, then you crush it, powder it, and put it into the analytical instruments. That was the idea originally. Because there you see from the side, although it's scratched from the coring process, you see how the surface of this core is. You see if there are concretions in it, if there are veins going through, if there are bigger crystals, and so on. So I would expect that they will take one core, the first core, possibly inspect it with the instruments,
Mhm.
and then take a second core from the same rock
Right.
and put it into the
You've got
cache.
comparable samples at that point that you can use, one for testing and one to look at.
Yeah, that's
Sort of like when you get toys, you keep one in package so it's near mint, and then you have one to play with as well.
yeah. The thing is, you want to avoid any contamination.
Sure.
And even if you possibly zap it with this laser, which ablates only microns each step, you want to actually have a pristine sample. Therefore, it depends on how the strategy is. But I was surprised that they put everything into it's more or less the trunk of the rover. I had expected that they actually drop it immediately.
Right. And that it would just be like sort of a cairn or a pile where they could then collect them from a later point in time.
So you leave the samples just behind and you drop it as soon as you have prepared it, because you never know if you survive a night. And if the catch rover has to crawl under this monster and somehow fiddle the cache samples out there, wouldn't be ideal.
No.
So these are all the problems that you have with caching, and yeah, I bet they have spent a lot of brainstorming how the approach.
I can only assume they've put as much thought into it as they did when they came up with that shock test of hitting a table with a hammer.
But that's straight up physics.
True enough. Now, we've got somebody joining us tonight. In our live streams, I'd like to sometimes bring in an undergraduate perspective. And so we thought this was a unique opportunity, again, pun intended, for somebody who had the curiosity and the perseverance, but might not have the spirit, to join us this evening. So let's bring in our roving reporter. Let's bring in Mel. There she is. How's it going, Mel?
Hello, I'm good. How are you?
How did you feel watching this afternoon's stream? Was it pretty exciting?
When everyone stood up and clapped, it was this moment. Like I'm sitting alone, and I was like, ah! Very exciting.
Well, it's interesting. You know, often we bring you on to get sort of the undergrad perspective, and I know that a lot of our undergraduate students, especially right now during the last little bit, have a hard time kind of struggling through their studies right now and realizing that there is an endpoint that they're trying to get to. And I think a project like this is probably quite inspiring.
Yeah, absolutely. Yeah.
So do you have any... Oh, go ahead. Yep.
Yeah, no, I was going to say it's really interesting to see like Dr. Gellert and be able to, be at the same university as somebody who has worked on Mars rovers. And it kind of like puts into perspective that these are not like out of reach dreams, Yeah,
this is actually so there are 10 instruments on this old. It's hard to get used to Curiosity being called old rover. There are 10 instruments there, and most of the instruments were developed by NASA centers, Ames, Goddard, JPL, and big institutions that typically have barbed wire around them. And that was always quite a nice twist that a public university like Guelph, we have our operations center directly beside 105. So whenever the folks take a break from their, not today or not in the last year when we went remote, but whenever they hit the bathroom, they have to crawl through all the students that are lined up for the next lecture. It's kind of a human touch of the having students directly beside the research that we do, and that's I think a good thing, because it's cutting edge science, but it is science.
Well, and I
Mhm.
think it's a uniquely Guelph sort of thing that occurs where, you know, you've got these people doing leading edge, like I said, world-class research that in this case is sending not just an object to Mars, but a high precision sensor that's actually going to tell us about what's on the surface of Mars, right in amongst with everybody with undergrads getting taught. And it's like you said, it's not some big ivory tower. It's accessible. There's this accessibility to it.
Yeah.
Mel, do you have any questions for Dr. Gellert?
So as I was listening to you kind of explaining how much goes into the landing and how much could go wrong,
Yeah.
I think what kind of came to my mind was, what if something does go wrong? Are there backup plans? Like, what's the protocol if something goes wrong?
The landing is unique. As I hesitate to think about backup plans. What if? So there are obvious no backup possible if the parachute doesn't deploy. So for this phase, there are little to none backups. Later on, when you're down and hanging on the bridle there might be, and I have no idea how the engineers at JPL do this. For example, they said, Obex, you mentioned it, that they have a hazard avoidance system for that phase. So think about it. How would you program the computer to say, okay, what is safe down there? Ultimately, if you dangle there for several minutes, it's like you're standing in front of the lake and you don't dare to dip your toes into the lake. You're screwed also. So there must be some kind of decision making. And in this landing phase, it's very sophisticated, and they will have played this through over and over and over again. Later on in the operation, the newer rovers, they actually have some more AI in it. So when you operate these rovers, you know, for example, from orbit you have a Google Mars, more or less, and you know we want to go in that direction. So you have a map, but you tell the rover, okay, this direction 100 meters. The new rovers actually drive likely a meter, look around, anything suspicious, okay, drive the next one. The old rovers, the MER rovers especially, they were less sophisticated in the decision making, and the team more or less programmed the courage of blind driving into them. Like, be very careful, like make 5 meters, then look around. Did you do progress? Yes, okay, another 5 meters. But that slows everything down. So with opportunity, we were driving across a huge sand field that covered the bedrock. And one day, we wanted to make progress. And so the courage was, the grade of courage was, close your eyes and put the pedal to the metal. So more or less gun it. And little to none stopping, looking around. And turned out the rover made something like 10 meters, and the rest, it got stuck in one of these dunes, and the rover wheels just dug itself in. It took several weeks or so to get it out. So these are the kind of decisions that the rover has to do, and that you have to program. What happens if there is a failure? For example, if you have in your daily plan to extend the arm, and you move the arm, and then you're measuring the currents going through the motors. And for example, if the motor current exceeds a limit or so, failure, stop, wait for assistance, more or less. So these are the kinds of backup plans, or stop and see and wait things that you program with these rovers.
Wow.
Yeah.
It's very interesting to hear about.
Yep.
Yeah.
I'm always surprised at what a slow process it is as well, because you think about it and you see something that basically looks like a robot tank, and you think about it on another planet. You think about it as being this big empty planet, and it hits and it takes off, and you're gathering information and you're taking video and you're doing sampling. Whereas in reality, you're only moving, are you even moving tens or hundreds of meters in a day?
Yes, but then you're essentially ignoring the landscape. You could literally drive by some Martian life form that waves at you, and you would ignore it. So, which is kind of unlikely, of course, but that's simply the point. Earlier, I watched CNN, and there was someone who completely justified said a trained geologist can do everything the rovers do in much less time. They go through the area with a hand lens and a hammer. They go look up the terrain and pick up a couple of rocks. Look at it with a hand lens. Possibly crack it open, grab a couple of rocks, put them in the backpack just beside the 6-pack of beer, which I was always told by geologists is the standard equipment for geologists in the field. And they can do so much more, but they can't do this on Mars.
Yeah, and I mean, is a backpack as good as a Mossbauer spectrometer? I mean, it's...
That's the other thing. Exploring the terrain by a trained geologist. They are trained to really read the terrain and the depths of all the outcrops and so on. You likely can beat it with a rover. However, they are trained in earth geology and mineralogy.
Yeah.
They know what happens there every winter. The snow falls.
Mm-hmm.
In the fall, the raindrops come down. So the geology on Mars has a different time scale. So none of the sophisticated instruments of the rovers, like a Mossbauer, like an APXS, you don't have this as a field geologist. So they make their first assessment, and they pack it in the back and analyze the samples in the lab later on overnight, or send it out to a laboratory. Hmm. But essentially, a trained field geologist would make much more progress, but to put 150 kilogram, including suit or whatever, field geologist, you need tons of material to keep the valuable field geologist alive and sane. And it's all a weighing of your options, and the rovers is the best we can do right now.
Well, speaking of ingenious devices, this rover contains a drone helicopter for the first time called Ingenuity. Sakshan, we have some footage of that. Can we show it? I wondered what your thoughts were about this, Ralf. We've got now this option to potentially observe from the skies upon Mars, as opposed to just rolling across the terrain. Is there any sort of marked advantage that a device like this can have that with information in terms of information that it can give us versus what the rover's been doing?
Oh, where do I start? We have actually whole groups of scientists who are assessing the maps that the orbiters take.
Right.
And they do an exercise called mapping.
I'm with you.
As a physicist, I didn't know what that is. But they kind of look at the texture of the ground and the elevation, and they try to see, okay, this area is the same height as this, and it has the same depth, so somehow they formed at the same time. So they try to read.
Okay, I see what you're saying. Yeah.
They try to read the terrain and disassemble the makeup of the different rock structures in there, and they want to take pictures and images of everything with the rover because it has a higher resolution than Google Mars or HiRISE, the high resolution camera from orbit. So they would love to strap a camera on the bottom of this helicopter and go up and take high resolution images of the surrounding of the rover.
I guess realistically, it's always going to be a better image than you're getting from these satellites, right?
Yes, sure. But if I get it right, this helicopter does have a camera, but it has no connection to the rover, so it doesn't take images and doesn't transmit it to to the rover. But that's, I think, what the ultimate goal of something like that could be. For example, if that thing was completely mature in 20 years or so, you would simply let it fly around and fly in all directions. Hey, drive around. Possibly you find something that we can't see from here, and then we drive there with the rover and do in situ, in detailed measurements. That's kind of what I think the ultimate goal of the helicopter is.
Sure. It's exciting to see more devices attached to this and as part of the entire mission itself. I think it's interesting to kind of have this idea that maybe it gives a little bit more of a touchstone for people where it's like, okay, when it was just a single rover or it's a single satellite that's taking images or whatever, now you have more of a team of robotic explorers that are kind of doing the
like
job.
A swarm of drones.
Well, yeah, I mean, effectively, right? So, I mean, if our ultimate goal is trying to find interesting samples or to find if there was something that looks like it has the potential that it could have been life years ago, having more devices up there probably helps.
Yeah, for sure. And it's if I got this right earlier, they said it's essentially a technical demonstration. They wanted to test this out. And how cool is this? They will for sure when the helicopter takes off, they will try to capture it with high resolution cameras and document with the rover the helicopter flying off. So that will be priceless.
Mm-hmm. Absolutely. And I mean, I guess we expect it to take quite a bit of time before we get any of the interesting high definition imagery or videography back to Earth. Yeah. Oh, we have a question in from the chat here. Let's take a look at this question. As viewers of our previous stream know, I'm very excited about this new technology that we're using to stream this because I can just bring these questions up. This one's from Christian Schultz-Nielsen. Do you have a sense for what the medium and long-term plans are in terms of exploring the surface of planets and moons in the solar system? What can young scientists look forward to?
there are these obvious goals like Europa, where there should be an ocean under thick ice. So, but the problem is it's about 5 to 6 times further away than even Mars. So,
Right.
In the beginning, over the next years, the moon is in high demand. So NASA and
I heard there's
everyone-
going to be a moon orbiting space station that's starting production.
Yeah. So the moon, Venus is way too hot to land there. So you will possibly have to hover in the upper atmosphere and sample there. Mars, an asteroid. Saturn,
Now, these are all projects that aspiring students can work with you on, right?
yeah, but just to more or less disillusionize everyone. So the very first mission that I was working on, as I said, I joined the Max Planck Institute in 1999. The very first mission was the Rosetta mission, where we built an APXS for this lander on a comet.
Oh, wow.
And so the order was, we built first it was an ESA comet mission, Rosetta. We built this version first, and was our breadboard, more or less, which we improved, which made the version on the MER rovers. And the original launch date was supposed to be 2003. It was supposed to launch from Kourou in French Guiana, but the rocket actually had a failure in the previous launch, so they scrapped this one launch, and they launched in 2004 or 5, I don't remember. So a year later, so the MER rovers actually launched first. But the Rosetta mission had to keep up or catch up with a comet, which are blast very fast when they are in the inner solar system. So this mission launched in 2005, let's say. And they had to do a couple of flybys around Mars, around Earth, and so on. And they landed in 2015, no, 13 or 14 on the comet. And it didn't work well. So with 3-legged lander, one leg was upwards, so it was a crash landing. But the overall mission to orbit a comet was successful. But it took 10 years to get there. So think about Mars is just around the corner if you can get there every 2 years in 6 or 7 months. So that's about the time scale that you have to think about when you're talking about exploring Titan, Europa, Io, or these further away objects, which are scientifically very interesting regarding life, because they're further out around a big gas planet, likely have oceans of methane or whatever. But it's challenging. So good luck. In this respect, Mars is really the obvious target where you can do neat science, but you get there in 6 months, and yeah.
Mel?
So I think this is a conversation that I have pretty often with people. So I wanted to get your take on it. how realistic is habitability on Mars? And when can we expect, if we can expect, man to land on Mars?
So you mean making a habitable place on Mars?
Yeah.
Actually, that is relatively straightforward. If you have enough resources, energy, and money.
Wow.
So the first thing you would want to do is dig a hole ground, like a cave in a cliff or so, to get protected from the radiation.
Oh wow.
Because Mars doesn't have anymore a magnetic field, so you get higher radiation doses on the surface. So you want to be protected there. You have to enclose everything. So it's like in a huge vacuum chamber that you fill with breathable air. So all this is really straightforward. Several things, for example, is up there. We know that there is water in the minerals. For example, the Opportunity bedrock. A student of mine, Mei Li, some 10 years ago, she looked at APXS data of the Opportunity rover, and Ian Campbell, retired professor emeritus, he at one point came up with a method to figure out how much possible water is in the APXS samples. It's one of these things. We didn't even know that this works, that this possibility to extract invisible X-ray invisible elements, amounts of elements from the spectra. But he figured out a way, and Mei Li estimated that there is about 10% of possible water in this dried out salt lake, still contained. So if you know that, and if you have a process that can extract the water from these bedrocks, you don't have to bring that much water. You just have to bring a machine and an energy source that extracts the water. You don't have to bring titanium or building materials or iron. Mars is chock full of iron. Has twice as much iron in the typical rocks that you can use to build structures. So this is all stuff that you can read out of the scientific results that we are working on with these rovers. That whole branch is called in situ resource utilization. It works for the moon. The moon has a lot of rocks that are high in titanium, which is a perfect building material, but you need to process the rocks. For this, you need energy sources that provide the energy that you have to use to process these materials. So these are all the kinds of investigation that you can do before you actually send someone up there. And
wow.
One of the instruments, I think it's called MOXIE, you showed it, Orbax, that makes oxygen out of the CO2, right? So it's more or less a prototype. Can you zoom in what's under MOXIE?
It says produces oxygen from Martian CO2.
Was I right? Was I right? I guess so, yeah. So the atmosphere is very thin, about 10 millibars CO2, 95% CO2, a bit argon, a bit whatever. If you can extract oxygen from there in a large scale, you can make a limited space, a laboratory up there, habitable.
Wow.
So They're
So
sky.
it's possible.
No, of course it's not impossible. No.
It's possible, yeah.
And
And what kind of time do we see a time scale for anything like this? Is this something that we might see a reality of in the next 10 years? Is Moon the first step? Creating like a moon base?
the moon,
As other countries deliver rovers and satellites to these different planets, I assume the space race will heat up again.
yeah. And I think that's a good thing. Competition makes you keep your step. Yeah. What's the time scale? I don't know. I'm just reminded I attended a conference in Berlin a couple of years ago where NASA and ESA were talking about a combined sample return mission. So the holy grail in Mars research is to get a cache sample, well characterized, well selected, interesting, pristinely back into an Earth laboratory. And they were talking, for example, how can we investigate and analyze the samples, for example, in the first step, without actually opening the welded seal so that we don't contaminate it. And they were talking about fascinating, from my physics standpoint, for example, going to a synchrotron and using high energy X-rays and gammas to penetrate the walls of the tube and to get images and information from the inside before you actually break the seal, because these are extremely valuable samples once they are back. Way more valuable and limited than moon samples, which are already very valuable. So what I took from the conference, just to answer your question, Orbex, about the timescale, while NASA and ESA were talking about, okay, how many grams or kilograms are we talking about to return to Earth and how to distribute them? The two last talks were from SpaceX and I think something Mars One or whatever. And they boldly presented, okay, we plan in 2025, we want to land this huge spacecraft on Mars equipped with 5 people and come back after 2 years. And then I thought, okay, why don't they just get a big box and grab a couple of samples and bring a lot of samples back? So these were the two approaches, one bold, Musk-like, explore and quick and bold plans, very ambitious, and then more, I would say, more realistic ones where you think everything through. So likely the future is somewhere in the middle from the time scale.
Exciting. Well, we've been at this for about an hour and a bit now, so probably getting close to time to wrap this up. I wanted to thank again for the viewers who joined us this evening, and also wanted to point out that both this and the previous live stream from this afternoon will live on our YouTube page and be on our Facebook page. So if you didn't get a chance to watch the live landing with us, then feel free to rewatch it and join along with the fun. As well, we do these physics live streams fairly often. Coming up on March 2nd, we have a medical physics one discussing professions in medical physics. And I wanted to give Mel a chance to ask her classic closing question before we get into that. But before we get into that, Ralf, is there any closing statements you want to make?
No, I'm happy.
Great. Fantastic. Well, we'll let Mel ask away.
So in your scientific career, Dr. Gellert, what has been your most exciting day of research?
Sol 1190 of Spirit. That is where we got possibly the most exciting sample back. So that was a sample where the rover exposed some white soil underneath the rocks, underneath the typical red soil. And we measured this, and we had measured similar things before, and they were chock full with water and with ferric sulfates. But this one was 90% silicon dioxide. And silicon dioxide glass, essentially, was one of the calibration samples. And when you look at X-ray spectrum, the spectrum looks actually boring because there's one big peak and nothing else. So we had this operation meeting with the Spirit team. And I think I said something along the way when I reported what we found there in the meeting, what to do next. I said, well, this is a boring sample. It's 90% silicon dioxide. The rest is a little bit dust, and titanium and chromium are strangely a little bit elevated. And I heard from the whole folks, I don't even recall if it was through phone or if we were still operating at JPL in Pasadena, they were laughing and laughing. I said, you nuts, this is textbook acidic leaching where water steam comes up through the crack of the rock, dissolves everything except the silicon, and the titanium and chromium are also staying there. So without knowing this, and I like it that I don't have much idea about geology, so I had no idea, but more or less you find something in the data of a physics instrument that measures chemistry. There's this textbook geology. So I like this kind of unbiased, not driven in any direction of your results research. So this, I like this very much. And this discovery actually by a scientist from another instrument, he proposed that this area where Spirit landed, Gusev Crater and Columbia Hills, that should be the landing site for the new rover because of that one discovery there. So we measured this to very extensively, and it was exciting because it could have been habitable, but NASA wisely decided to not go back to an already known landing site. However, I would have loved to see the new rover coming up and seeing there the old Spirit rover, dusty, sitting there for 10 years. When the new rover would spot its predecessor. I would have loved this, but the new landing site is even better. So that was my favorite discovery and favorite day.
That was a great answer.
Well, I'd like to do one final round of thanks. Thank you very much, Mel, for joining us and coming along with us on this journey and with the questions that you had. I'd like to thank Dr. Ralf Gellert for both streams today and for giving an insight that's truly a unique insight into somebody who's sent 3 different sets of equipment to the Red Planet. I'd like to thank very much, I didn't get a chance to thank him the last time, but I'd like to thank our producer, Saksham Sharma, behind the boards for making this run smoothly and wonderfully. And I'd like most of all to thank all of our viewers who stuck along for this incredible journey with us. And hopefully we'll see you on March 2nd for our discussion of medical physics. Until then, if you get an opportunity and you have the spirit of the perseverance and you're generally curious, then give us a like and a follow and a subscribe and all that other stuff. And until then, I hope you have a science-tastic week. I'm the Great Orbax, and this is the University of Guelph Department of Physics live stream signing off.